Okay, piecewise functions. Okay. Yes, it is as much fun as it sounds. Piecewise functions. Well, this is one of these deals that sounds weird, looks even weirder, but is actually used quite a bit in the real world. You know, you're always looking for real world applications of certain things. This is one of them. For example, they've got one here, monthly charge for power. If you use so many kilowatts, you get charged at this rate. If you use more, then you get charged at a different rate. And then if you use way more, you get charged at even a different rate. This is standard operating procedure for companies that sell power, residential, small business, farm, large companies. They get, it's like buying in bulk, so to speak. So, let's try this one. It says postage paid for a first class letter jumps by 20 cents for each ounce after the first ounce, but does not increase until the weight increases by 1 ounce. So it goes up 20 cents. So if we look at this here, for anything that goes from 0 to 1, it's 44 cents. 64 cents from 1 to 2, 84 cents from 2 to 3, 104 cents or $1.04 when it goes from 3 up to 3.5. So they've got the table sitting over here in the form of an XY chart. And if we go through and take a look at the graph of something like this, it looks like this. What this is called a step function. You're always going to pay a certain amount at a certain level. So say, for example, if you had a letter that you were, or an object that you were mailing that was 2.5 ounces, you pay the same thing as if it was 2.25. Likewise, if it was 2 3/4. Anywhere in that range, it's going to be the same. So now as we go through this, we are going to get something that looks like this. We want to graph this function. Now, you know how to graph 5x boost. You know how to graph x cubed. That's not a problem. Except now that they are going to identify the range, or I should say the domain upon which you are going to have the functions. So, look at that. It stops and then it goes to something else. So, from what I see here, closed circle at 0, because we got less than or equal to. Let's try that a little bit more. Is that better? And it goes up to 3. Okay, we've got a graphable line going from 0 to 3. That's all we can graph. Anything that is above 3 up to 5 gets put into the other function. So really all it's doing here is telling you, hey, if you got a number that's between 0 and 3, use this. If I've got a number between, or 3 to 5, use that. No other numbers are identified on this because we don't have any other information on what should be used as a function. That's all it is. So, residential power costs, you've got that. What does this one look like? So let's try this. Let's technical difficulties. It's probably because it's all right. So what they want us to do here is they want us to write the piecewise defined function that gives the monthly charge for residential electricity. Okay. So if I look at the first part here, this is on the monthly kilowatts from 0 to 65. So I'm going to start off with that idea. So we've got, let's see, X, let's see, less than or equal to up to. Now, when it says 650, is that greater than or equal to, or less than or less than or equal to? In other words, is 650 included? It's included, and if you have a question, you go down to the next line, it says more than. So that implies that, hey, we got to do this, 6, 5. Now, what is the function going to look like for this? Well, it's going to be this weird looking number, right? Plus what? 750. So sometimes when you're writing this out, you're going to get some really large things to deal with. So I start off with 0.045991. Do I want to round that? Absolutely not, because that's what they're charging. It's like going to the gas station and you look at it, oh, we're only paying, it's $1.99, but it's really not $1.99, is it? It's really $1.99.9. You get that extra, 9/10 of a cent out of it. So, X plus 700, $7.50. Are you always paying that $7.50? Even if you use absolutely no electricity, are you paying that $7.50? And the answer is yes. That's more or less just a service charge that goes along with it. So, I've got that information there. Now, it says 37.40 plus that per kilowatt hour. Now, one of the things that I want you to keep in mind here, where'd that 37.40 come? If I were to do something like this, calculator real quick, and I were to go and take 0.045991, multiply it by 650, and then add $7.50, what do I end up with? Do I end up with approximately $37.40? So, sometimes depending upon how they identify the charge, I've seen situations where it wouldn't say this, it would just identify this per watt above 650. Then you need to identify what the previous is. Now, another thought that goes with this one is, have I paid for at least 650 watts? So if I've got 0.03946 and X is the number of kilowatts that I have, does this 37.4 include what I've paid already? I just calculated that out, and that's what I get if I use 650 watts. So, do I want to pay for it all over again? No, I wouldn't want to. So would I have to go and take X minus 650? Would I have to go and take off what I've already used and paid for? Because I only want to consider what is extra. Okay? I only want to go over that. So, what's this going to be? Well, this would simply be just 650 less than X less than, and it goes up to what? 1,000. Kind of running out of room here. So back to here, and I've got 1,000. So if I take a look at this, is that 5121 probably what I would pay if I used 1,000 kilowatts? Based on the information that I have been given, would that be, or wouldn't it be? Should it be? I would like to think so. So that means that we are going to have 0.03837 x minus 1,000, because I've already paid for 1,000 kilowatts in that idea of $51.21. And then x would end up just being x greater than 1,000. So it's not really all that bad of an idea. It is just more complex and it's got more bits and pieces. But this is pretty close to reality. This is something that you would definitely have to look at dealing with. In actuality, cell phone plans, when we first started off with them, was based on this kind of a system. You paid this much if you used this much.
Good morning. I apologize for the interruption. There is a college rep from North Dakota College of Science in the library now. Anybody is interested in speaking with her, please go to the library now or when your teacher dismisses you.
So, what does it mean if I have to use C of 950? Well, C of 950 would mean that I've used how many kilowatts? 950 kilowatts. So if I use 950 kilowatts, which one of these do I have to use? The red, the blue, or the purple? Blue. Why? Because that's where 950 sets in. So I'd plug in 950 for X, subtract off 650. Right? Then I'd have 300 kilowatts left, multiply it by that, add 3740, and I got my charge. Okay. What about the charge for using 1,500 kilowatts? Red, blue, or purple? Purple. So that means I would end up putting that in there, subtract off 1,000. So that would end up being, calculator on, so we would end up having, what is it? It's going to be 0.0383737 multiplied by 560, yes? Yeah, that would cause a wee bit of a problem, right? Nope. Right? Yep. So, that's another $21 plus the base charge of 51.21. So that would be $72.91 or 90 cents. That's what it would cost me for using 1,560 kilowatts in a month. It's not all that bad. It just requires some time to think about and understand what's going on. So you got to learn to assimilate the information that they've got. Wind chill factor. Ooh, cheese whiz. That's really good for today, isn't it? Okay. Wind chill factor. Depending upon the temperature, depending upon the wind speed. Yeah. Wind chill factors are used to measure the effective combination of temperature and wind speed on human comfort. By providing equivalent air temperatures with no wind blowing, one formula that gives a wind chill factor for 30-degree Fahrenheit temperature and a wind velocity v in miles per hour is given to you as such. Now, if I take a look at this, I've got different functions that I would have to use. So, Find the wind chill factor for the 30-degree temperature if the wind is 40 miles per hour. Does this work for our 20 below this morning? And the answer is absolutely not. Okay. Why? This formula is set on a 30-degree temperature. If I wanted to find something for our current, I would have to look that up. I would have to go and find another formula. Because when you read it here, it says one formula that gives for 30-degree temperature. Now we see here, if there was absolutely no wind today, it would have to be 30 degrees, right? So if there was absolutely no wind out there and it was 20 below and I tried to use this formula, it would tell me that's 30 degrees outside. That doesn't make a darn bit of sense, does it? So you have to read into the situation and be aware of what it is. Don't just sit here and look at it, oh, it's a problem that I got to answer. What is the context of the problem? More often than not, it'll go and lead you to how to solve it once you understand the context. All right. Service calls. Okay. What's happening? Cost of a weekend service call by AirTech Services is showing it right. Write a piecewise defined function that represents the cost for service during the first 5 hours. Okay, well, how much is it going to cost you for 1 hour of service? By the chart, it'll cost you how much? For those of you actually looking at this, that's $330. What happens if I've got an hour and a half in there? How much is it going to cost me then? Hour and a half? How much? $550. So you mean to tell me that if they're there for an hour and a half, it's going to cost me $200 more than if they just could have gotten done in an hour? They were probably talking a little bit more to get that extra time in there, right? So if it took them 5 hours to fix it, it cost me $770, right? Which actually, if you think about it, is a better deal per hour, isn't it? So when you're looking at this, understand the context of the problem. Put yourself in the situation if necessary. Now, there is another function that we've got, it's called the absolute value function. Okay. Its graph is always going to have this quality to it. Okay. So, here's the absolute value equation. They have that up here. So we're going to kind of walk through solving some of these here so you can see what the situation is. So, supposed to solve the following. Now, the idea here is that first off, Ann, what value, if I take the absolute value of it, would equal 9? I heard something. A 9. So the absolute value of 9 is 9. Good. Is that the only one? No. Negative 9. So what we end up doing here is this. We would say that either x minus 3 is equal to 9 or x minus 3 is equal to negative 9. Those are the two possible values, right? Add 3, x is equal to 12. Add 3, x is equal to negative 6. So, there are two possibilities here for this one. X is either equal to 12 will work, or x equal to negative 6 will work. all it is. What about the next one over? Well, 2x minus 4 is equal to 8, or 2x minus 4 is equal to negative 8. Those are the two possibilities. Add 4, 2x is going to be equal to 12, divide by 2, x is equal to 6. Add 4, I sound like a broken record. Divide by 2, x is equal to negative 2. So those are the two values. That would make that happen. Easy enough. We just simply go through and follow the rules that we have. So, what happens if I've got this one? Well, that means that x squared minus 5x is going to be equal to 6, or x squared minus 5x is going to be equal to negative 6. Those are the two possibilities, right? And now we've dealt with quadratics before, so we know that it's going to be x squared minus 5x minus 6 is equal to 0. This factors out as, let's see, this one's going to end up having to be x, let's see, minus 6 and x plus 1 equals 0. Is that the correct factorization? Get negative 6 plus 1x, negative 5x, so we got that. Always check the outside and the inside to see if you actually add up to that. So that means x minus 6 is equal to 0, x plus 1 is equal to 0, so x is equal to 6, and or x is equal to negative 1. So those are two possible solutions that would actually make this work. Let's just check that for a second. If I go and put 6 in here, what's 6 squared? Well, that'd be 36. I put 6 in here, that's going to be minus 30. Is 36 minus 36? Yeah. Let's try the other one, just for the sake of argument. If I put in 1 squared, or negative 1 squared is 1, last I checked. Let's see, negative 1 times negative 5 is 5. 1 plus 5 is 6. Yes? So, what's the next one? Well, same idea. X squared minus 5x is going to be equal, whoops, sorry. Plus 6 is equal to 0, yes? So now for this one, this is going to factor out as x and an x, addition and addition. No, not two additions. It's got to be two what? Two subtractions. Subtract is equal to 0. Why has it got to be subtractions? Well, this is positive, so they've got to be the same. So what factors of 6 add up to negative 5? That'd be a 2 and a 3, right? So here we go. That means that x minus 2 is going to be equal to 0, or x minus 3 is equal to 0. X is equal to 2, x is equal to 3. Plug it in. 2 squared is 4. 4 minus 10, well, it's negative 6. Plug in 3. 9 minus 15, well, that's negative 6 as well, right? So it does take a little bit of writing out. It's not that big of a deal. It's just going through and doing the algebraic manipulation. But the biggest catch is starting off and knowing that you've got to set this and that. You've got to set those two things to begin with. So, power functions. Now again, these little beige boxes, make sure that you actually go through and put those down in your notes so that you have a record of them so you know what they are. So when they say, hey, use a power function, you know what you're looking at. Now, if we're looking at these ideas of a power function, essentially what they are, kind of looks like a quadratic, doesn't it? y is equal to x squared, y is equal to x cubed. Hey, we've seen these things before. We know how they work. Not a big deal. But now we can also get some really weird looking things in there. This is the 2/5 power. So when I look at this, or the 2/3 power, sorry. So that's got kind of a weird shape to it. We've not seen something like that. So that's what it does. Okay, here it's 3/2. Notice that these kind of look like a reflection of each other across the diagonal. Little things to always go through and notice when you're working on these things is patterns that you see. Now, wingspan of a birdie. At 17 feet, the wingspan of the prehistoric bony-toothed bird may exceed that of any other bird that ever existed. Animal weighed about 64 pounds and soared the Chilean skies 5 to 10 million years ago. Wingspan of a bird can be estimated by using the model. So you use this in biology to determine whether or not, or I should say, based on a wingspan, or based on its weight, what the wingspan should be. Where L is the wingspan in feet, W is the weight in pounds. So if I were to go and graph this thing out, that's easy enough. Calculator on y is equal to, what do I want to put in? 2.43 x to the 0.3326. Now, window. Is it possible to have a negative weight bird? No. So obviously it's got to start off with 0. Now we want to take into account this thing, and said the animal weighed about 64 pounds. So let's go up to 100 pounds. We could have a 100-pound bird. And let's see. That should just about do it for us, right? Oh, y minimum. Can't have a negative wingspan, can we? No. 0. So they say a 17-foot wingspan right there. We'll go 25 since we graph. So there's my graph. Okay. Trace. 64. Okay. So did it actually work? Well, it didn't. At 64 pounds, he should have had only about a 10-foot wingspan. That thing was 17 feet. No wonder why it died out. It didn't fit the model, did it? Now, what happens if something weighs, it says the wingspan of a mute swan, 40 pounds. So if I put in 40 on the trace, I get an 8-foot wingspan on that swan. Okay. Let's see, it says the albatross, the weight of an albatross whose wingspan is 11 feet. Well, if I want to, I can just do this through it here and kind of see, where do I get 11? Keep going, keep going, keep going, keep going. Okay. 11 feet, 4 inches. 4 inches is approximately a quarter, right? So if I hit it one more time, I get 1.62024. So, thing would have to weigh 100 pounds to get 11 feet, 4 inches. Ever seen an albatross? Can't say that I've seen an albatross, but I guess they're fairly large critters. Let's see. Goose. You guys go goose hunt? Who goes goose hunt? Sort of, kind of, maybe. What's the average wingspan on a goose? Go goose hunting. What's the average weight for goose? Nothing. do you actually think that this model works well for all birds? What about a turkey? You get that good old 20-pound turkey that's dressed and ready to go, so probably weighed a little bit more. So if you got a 25-pound turkey, let's see, should have a wingspan of 7 feet. Is that realistic on a turkey? Does a turkey fly? It not. So again, it's an estimation. You'd have to do a lot more modeling out there, you know, collect birds, measure their weight, measure their wingspan in order to develop this kind of a formula. So, root functions. The type of function that we have got to deal with. Now, notice that this one kind of looked like that other one that we had there. Remember, when we're dealing with something that is fractional or a decimal value, that is going to represent a root. Okay. Now, square root happens to be, half. If it was to the 1/3 power, well, that would be a third root, which would be what I'd be looking at over here. So, it's just a different way of writing out what the roots are. There is also the reciprocal function. Okay. Looks like that. Creates a graph like that. Variation functions. Notice these are all kind of variations on a theme. You guys don't like my jokes. Y is equal to k x to the n. It's a variation equation because there's some constant that's in there. You have x raised to some number n. So, inversely proportional. Some more. Now, I highly recommend that you go write these things in your notebook so that you've got them. And if you want, so that you can have an idea of what each one looks like, set k equal to 1 in this case. Graph it out, see what it looks like. So that when you're looking at these, you've got kind of a ballpark idea. A lot of times, like with the reciprocal function, if you see a graph that looks like this, it leads you to the type of function that it is. That's why it's really important to go and take your data, graph it out to see what it is that you've got. So when we're talking about the model that we're working on, you can take the data that you've been able to compile, put it onto a graph. What shape does it make? Is it linear? Is it not linear? Leads you down that path. But like I said, make sure that you get these written down for examples of what the graphs look like. So, I'll let you guys get to work on this.